Since TCP offers end-to-end congestion, we must compare it to the network-assisted congestion control as provided by ATM. In this module, we shall understand how TCP window operation works that helps us not only to implement flow control, but also congestion control. How these loss and delay events notify the TCP sender of prospective congestion, and how the congestion window affects the effective data rate that the user gets while using TCP. Again, the figures and some of the text has been borrowed from Kuros and Ross. The end-to-end congestion control works without network assistance. It is transparent to the intermediate routers and switching fabric. When TCP implements congestion control, the sender maintains a congestion window, that is, the last byte that has been sent and the last byte that has been acknowledged. Both of these are going to determine congestion window. If what has been sent has been acknowledged, congestion window can be as large as possible. But if what has been sent has not been acknowledged, it means the congestion window is going to grow smaller with time. Congestion window is therefore dynamically a function of the perceived network congestion without asking the intermediate devices of their buffer occupancy. TCP infers the happening or the incumbent congestion through either the loss event, which is when there is a timeout event taking place. A packet was sent, but the timer for that packet timed out and no acknowledgement arrived. Or 3 duplicate acknowledgements arrive. When 3 duplicate acknowledgements arrive, it indicates that one of the packets has not been received, is stuck somewhere in the middle. So duplicate acknowledgements are telling the sender a good news that packets are getting delivered, but some of the packets are getting lost. So we can see that the timeout interval tells of a very grave picture, whereas the arrival of 3 duplicate acknowledgement tells that congestion is building up. TCP sender reduces the congestion window after loss event, and it reduces down to 1 and starts from the slow start mechanism. If TCP sender acknowledges or gets to know of the arrival of 3 duplicate ACKs, it means that the congestion is slowly building up, so it must not exponentially increase its congestion window and must resort to conservative increase in window size. So 3 mechanisms are incorporated by TCP post-congestion. That is additive increase, multiplicative decrease, slow start, and conservative window enhancement after the timeout event. So if you look at this figure, on the x-axis we have time, on the y-axis we have varying congestion window. It is averaging around 16 kilobits per second, but it goes as high as 20 kilobits per second and as low as 8 kilobits per second. It means that the window keeps on fluctuating between either 24 kilobytes worth of data or 8 kilobytes worth of data. With this increase or decrease in the overall congestion window, the effective rate that the user is going to experience is now a function of how much time it takes for the acknowledgements to arrive. That is determined by the round trip time and the congestion window at various time instances. So the rate is the congestion window represented in kilobytes and the time it takes in round trip time, RTT.